So alkenes are unsaturated hydrocarbons. They have the general formula CnH2n. We know that alkenes have a double bond. The carbons which are involved in the double bond have the hybridization of sp2, and this is why the shape of the carbon involved in the double bond is planar. It's flat. The bond angle in the double bond is 100 and around 120 degrees. There is a sigma bond and there is pi bond. So the simplest alkene we know is ethene or ethylene, and it has two carbons with a double bond between the two carbons and four hydrogens. Because it has a double bond, there is no rotation about the double bond, unlike the sigma bond or the bonds in alkanes. So in alkenes, there is no rotation around the double bond. So let's talk about the structure and bonding of alkenes. So we said that ethylene is planar and the bond angle is close to 120 degrees. Actually, the bond angles are not exactly 120 degrees, but as you see here, the bond angle between the hydrogen, carbon, and carbon is 121.4 degrees, and the hydrogen, carbon, hydrogen here is 117.2. These bond angles are to ensure that the atoms are furthest away from each other in space in order to avoid any repulsion between the bonds, between electrons and the bonds. The two carbons in ethene are sp2 hybridized. So we talked about hybridization before in the last lecture when I posted a video about hybridization. But let's just recap for alkene. What is sp2 hybridization? So we know that for carbon there are 6 electrons in total. We said 2 electrons in the 1s orbital. And there are 2 electrons in the 2s orbital here, the one in red. So there are 2 electrons here. And we have 2p orbitals as well. So we have the 2px, 2py, and 2pz. So 2px and 2py both have 1 electron, but the 2pz doesn't have any electrons. So to form the sp2 hybridization, the 3 orbitals will combine with each other and form 3 new molecular orbitals or hybridized orbitals. These hybridized orbitals are called sp2. sp2 because there is a combination between one s orbital and 2p orbitals, so it's called sp2. And if you look at these new hybridized orbitals, they look a bit different from the unhybridized ones. So the unhybridized one each has 2 equal lobes, but now the hybridized orbital has 2 lobes which are not equal in size. Now each of the 2 sp2 orbitals will only have 1 electron, and we will have the 2p orbital remaining here, which originally didn't have any electrons. Now it has 1 electron as well. So now we end up with 3 similar equivalent or sp2 orbitals, hybridized one and 1p orbital. If you look at the energy of these orbitals, the 2s orbital has lower energy than the 2p orbitals here. So this one is lower in energy. Now the 3 sp2 orbitals will have higher energy than the 2s orbital and lower energy than the 2p orbitals. The 2p Z orbital remaining here at the end will still have the same higher energy as the 2p orbitals. It will be higher energy than the other sp2 orbitals. Each of the sp2 orbitals will have 1/3 s character and 2/3 p character. Now the bond that will result from sp2 orbital will be shorter than the bond that results from the sp3 orbital because it has more s character, so it's more closer to the nucleus. So we know that one p orbital will remain unhybridized. So the three sp2 orbitals will be arranged in a flat form, in a trigonal planar form, all the sp2 orbitals here. So these three ones, trigonal planar, and the bond angle here is 120 degrees. And if you look here, you will find the 2p orbital, the unhybridized one, this one in pink and blue. This one, it will arrange itself to be perpendicular to the plane of the three hybrid orbitals. So the angle here between the 2p orbital and the sp2 orbitals, the plane of the three sp2 orbitals is 90 degrees, so it's perpendicular to them. Each of these will only contain one electron. So what about the bonding? How does the bonding take place? So first of all, this is the carbon atom, the sp2 hybridized one. The three green lobes here represent the sp2 orbitals, and the one that is in red and blue here represents the here represents the p orbital. Now we have two hydrogens. So for ethylene, we have two carbons. Okay, each is sp2 hybridized. And we have two hydrogen, each has one s orbital, one electron in one s orbital. So the head-to-head overlap between the 1s orbital of hydrogen and the sp2 orbital of the carbon will will give a sigma bond. So two sigma bonds between the two hydrogens and the two sp orbitals for each carbon. And then we have the sp2 orbital, the head-to-head overlap also between the sp2 orbital of the first carbon and the sp2 orbital of the second carbon will result in another sigma bond. So there is a sigma bond here, sigma, sigma here, here, and here. So you end up with 5 sigma bonds. And then we are left with the two p orbitals in each of the carbon. So now there is the side-to-side overlap between these two unhybridized orbital will form the pi bond. So the pi bond here formed from the side-to-side overlap between the two p orbitals of the carbons. Now you end up with ethylene that has double bond between the two carbons. One of them is sigma and the other one is a pi bond, and each also have two hydrogens with sigma bonds. This is the hybridization state of alkene and how the bonds are